What I'd like to do today is talk to you about pulse oximetry. So I'm going to try to bring together a variety of different things that we've talked about and revisit something that we saw at the very beginning of the course, which was that little pulse oximeter that you stick on your finger. Okay? We're going to go into some of the specifics of that. And then, if we have time, I want to hear from the two groups that I've already presented. I'll show you some pictures of what they did, and we'll hear from them how things went. Okay? Okay. So pulse oximetry. What is pulse oximetry? So, as you guys remember, that pulse oximeter measures the percentage of oxygenated hemoglobin in a person's arterial blood. Why do we care about arterial blood versus venous blood?
Arterial blood is directly oxygenated.
Yeah, so the arterial blood, when we breathe in, we get oxygen in our lungs. That oxygenates our blood, which is pumped through the arterial system. So that's the blood with fresh oxygen. Goes through our bodies. Oxygen gets taken out from the different tissues and cells that are near all those little capillaries. I don't know if you guys remember, but the arterial system is kind of these thick tubes, muscular tubes that help push along. The heart gives the big push, and then they also are muscular and help the blood come through. Then there's this, what you normally see in a picture is this capillary system with little capillaries that get really small and then touch each other, and you get a lot of passing of oxygen into the cells that need the oxygen, and then also passing of carbon dioxide into that blood, and then that comes back to the venous system, right? And then that goes back to the lungs, and the whole cycle starts over again. And we do this 80 times a minute, 60 times a minute, depending on how fast our heart beats. Okay? So, you can measure the amount of oxygen, percent of oxygenated hemoglobin in the blood in a variety of different ways. You basically need a spot where there's blood, which is pretty much a lot of spots on our body. Okay? And you need the light to be able to go through it. So, if it can make it through our finger, it can make it through an earlobe pretty readily. Okay? Some things you might not think about is you can do it from the top of the ear, you can do it on the nose, you can do it on the foot, you can do it on the palm and other sites. You can actually even do it through the eye. The eye has quite a bit of blood, and you can actually shine light through and see the light comes back. So it doesn't always have to be, as you hopefully discovered in your experiment with plants, you can get some similar types of behaviors, whether you're going through or whether you're reflecting. Okay? You can get some of the similar kind of data. So, it can be measured by a light transmittance, that's the most common, or by a reflectance, just like I mentioned. And it gives you a percentage of saturation and the pulse. Now, just to give you a sense of what that percentage means, if you have 100 hemoglobin molecules, most of them have 4 molecules of oxygen. Some have 3, some 2, some 1, or none. Assuming that a total of 380 oxygen molecules are bound, you had 100 hemoglobin, so the maximum was 400 that you could have bound, and you have 380, then you would have 95% oxygenation. That makes sense? Okay, now in the body we have a heck of a lot more hemoglobin than 100 molecules of hemoglobin. We have billions and trillions of hemoglobin molecules. Somehow that little machine can figure out what percentage of them are oxygenated. Does it count them? That would be horrible, right? That would be like the most painful approach possible. It doesn't count them, but it can overall figure it out based on optical properties of what happens to different types of light when they go through. And by the way, these devices that measure this is the one that you're most familiar with. It goes on the finger. You guys remember seeing this? There's also other ones that can go on the wrist. There's ones that are bigger machines, which then have a piece that comes off of them. In the hospital, they use one that looks... Yes, Bo?
What's the ideal saturation of human?
100%. Yeah. Some of you had that. I unfortunately do not. I'm more like 97, 98. It tends to be that as you get older, that percentage tends to go down. Now, if you're quite the athlete and are constantly exercising and being very active, chances are it's going to be higher. Okay? But when you're young, chances are that it's going to be high as well, unless other activities that you engage in might cause problems in the oxygenation of your blood, or you just don't have that efficient of a system. Yeah, there you go. So in the hospital, these devices look more like a box. And actually, if you guys are curious, I have pictures later on because recently I had to make some visits to the hospital, not for myself, but for others, and I took pictures of all these things. But they are bigger machines, and they come off with a wire and a little Band-Aid looking thing. Okay, during the break I have the unit, because some of them are disposable, and I'll show you what that looks like. But you'll see this very, very often when people are in the hospital. You see this Band-Aid looking thing on their finger, and that's what it's doing. It's measuring the oxygenation, and sometimes it can be more complex of a device and measure a variety of things. But let's think a little bit about what blood is. Okay, so what are the main functions of blood? Okay? Supply of oxygen to tissues. So the oxygen gets bound to hemoglobin in what's called cooperative binding, which means that it's easier once you have one oxygen bound to bind the second one. It's even easier to bind the third one, and then it's even easier to bind the fourth one. Okay, it's cooperative binding. The more you have bound, the more it wants to bind others. And blood is very important in doing that. It's one of the primary functions. But it's also important to supply glucose, sugars, amino acids, all those things, and fatty acids, which is dissolved in the blood or bound to plasma proteins. It's also really important for removing CO2 and other wastes in your body. It has immunological functions, including the white cells that run through there, detection of foreign materials by antibodies, coagulation. So when you cut yourself, the blood is important in getting the right proteins there so they can form a mesh that can then block more cells from escaping. And then you can actually get the scabbing. And first coagulate and then you get the scabbing so that you stop the bleeding. It transports hormones and the signaling of tissue damage. So your body actually knows if something's wrong with it. It sends signals to the rest of the body so that the body can prepare for it and take care of it. It helps you regulate your body pH. And as we've also measured with a thermometer, it helps you regulate your body temperature because it can take excess heat from one area and bring it to the rest of the body. Or if your extremities are cold, it can bring blood to your extremities, increase the amount of blood to your extremities to warm up your extremities. Or in the case of stress, it can deny blood to the extremities and actually keep the temperature warm in the core areas. So there's different ways in which blood plays a part in this. Now, blood is 45% cells by volume. So if we were to take some blood out of your body and separate how much of that volume of blood, let's say we took a liter out, which would be quite a bit, how much of that would be cells, and about 45% would be cells. And out of those cells, 96% are red blood cells, 3% are white blood cells, and 1% are platelets. So red blood cells are quite a bit. The other 55% of the volume is blood plasma, which is mostly water, then with some blood proteins and inorganic electrolytes. So inorganic electrolytes are what? What do they mean when they say inorganic electrolytes? Salts, buffers, okay? And the plasma is a yellowish color. So you guys might have heard before where they separate cells from plasma. I mean, yeah, and you get this yellow bag and you get the red bag. Because sometimes people just need plasma, other times they need the blood cells, sometimes they need the whole stuff. Okay? So, under normal conditions for humans at rest, especially younger humans, hemoglobin in blood leaving the lungs is about 98 to 99% saturated with oxygen. Okay? And the blood coming back is approximately 75% saturated. So what that means is that when the blood is first going through the lungs to get oxygenated, it ends up getting about 98, 99% or 100% even oxygenated. And then as it goes through the body and comes back to the venous system, the stuff that comes back has lost about 25% of its oxygen. It still has about 75% of its oxygen left. Okay? Now, in a trained athlete, this is really interesting, the saturation of the venous blood, the blood coming back, can get as low as 15%. Okay? And this is really interesting because it means in a trained athlete, their body is very, very good at getting as much of that oxygen out as possible and into the body. And why might you want that? Why might you want that better capability of taking out the oxygen from the blood? more efficient, okay? And you're very active muscularly, right? If you're a trained athlete and you're engaging in your activity, and you want as much of the oxygen to help you with your cells, to give energy to the cells as possible. So, usually, in most of us, any condition which leads to a sustained mixed venous saturation of less than 50% will be poorly tolerated. So basically, if in our bodies that are not used to being very athletic, and I can't speak for all of you because some of you are very athletic, if you get that really low percentage coming back, then something's wrong with you. But in a trained athlete, they can be that effective at getting the oxygen out. So I'm having some problems with lighting. So the other thing, oxygenated blood is bright red, and this is due to the oxygenated iron. It's basically rust, okay? It's like the color of rust. Rust is this deep red, and you get really nice, good rust, clean rust. Okay, deoxygenated blood is a darker shade of red. So that's kind of the differences in color between oxygenated and deoxygenated. It's not red and blue. Remember we talked about this before? We do not have blue blood, okay? Blood looks bluish in some people. The venous blood tends to look bluish. It's closer to the surface. That's mostly because of the way that the fats and other parts of your body interact with the light and the way the light is reflected. Okay? It's not the color of the blood inside. So veins typically appear blue in color because of the way light penetrates through the skin. Okay? Now, why do they make it blue? When they show it to you in medical charts and your anatomy, why do they do that, do you think? More distinguishable. It's more convenient. Okay? And because people saw their veins as appearing bluish, that's probably why they picked the color blue. They could have picked yellow, they could have picked purple, they could have picked whatever they wanted, really. But they probably picked blue because people were used to seeing that. Okay? Just that simple. And also, they had to pick a contrast in color because when they injected animals to study, venous systems versus arterial systems, this was more easily distinguishable, these two colors in the animal you were about to dissect.
I was wondering, when you got all dry blood, that darker color, and the oxygen blood is actually blue, you have blood that's dry and folded, turned blue.
I think there's other things going on there. I think there's also breakdown of some other things inside the blood. Blood that, when you just cut it and it's oxygenated, it's exposed to oxygen, it has that bright red color. Over time, it tends to change somewhat. But so I don't know if maybe that's... There's so much other oxidation that happens and other breakdown reactions that happen once blood is out for a while. Then I'm not sure what all that chemistry is. But you're right, it does get darker. Okay? So, this is what hemoglobin looks like. Okay? Now, it doesn't actually look like beautiful little spirals of blue and red. Okay? As you guys are growing increasingly aware, we make up stuff all the time. Okay? This is how scientists have to represent stuff. Okay? So, the way they like to represent certain types of repeating structures of amino acids is through spirals, and the way, if you want to get a really pretty picture, you make those into ribbons. Okay? This is the more ugly way that we like to see things, but very descriptive. This is only the heme group, only the central part in here, showing you what's happening there with the iron. But we like to make these kinds of diagrams because they help us visualize a three-dimensional structure. Now, this is the oxygenated form, and what you see, the oxygenated versus deoxygenated, it looks like this. This should be animating, but it's not animating right now. I'm sorry about that. Let me see if for some reason... No. That didn't do it. This is the oxygenated form, but it actually changes shape as it gets more oxygen. And that change in shape between deoxygenated and oxygenated hemoglobin, that change in shape actually makes it easier for more oxygen to be grabbed on. Okay? So it's harder to get the first oxygen, the second oxygen is easier, third oxygen is even easier, the fourth oxygen is a little bit harder, but still not that hard. Okay? So the shape of the hemoglobin actually changes as more oxygen is bound. Okay? And that's what leads to this cooperative binding. So, each hemoglobin contains 4 hemes. This is a heme group right here. And the oxygen is bound cooperatively, as I just mentioned. And the most important thing for us in biophotonics is the visible and infrared absorption changes with oxygen binding. Okay? And you guys know that intuitively because if the color changes, that means that somehow the interaction with light has changed. Okay? Does that make sense? And here's the proof. Okay? So, what you see here is the hemoglobin with oxygen. And sorry for the color choices here. This is not a good color choice because blue and red and they're opposites and all that kind of stuff. This is a chart that I found somewhere. Not the best color choices. But what you see is, here's the wavelengths. And what are the wavelengths around 700? What color is that? Red. Okay? Okay? So, if we said that red, that blood with oxygen is bright red, and blood without oxygen is dark red, would you expect more light to be absorbed in the red region by oxygenated blood or deoxygenated blood? What would you expect? Sorry? You would expect the oxygenated to absorb more of the red light? If something looks a color, what does that mean about the light of that color? Is it absorbed or reflected? Reflected. So if something is more of that color, would you expect it to absorb more light or less light? Less. And here it is, oxygen. Hemoglobin, oxygenated hemoglobin is absorbing less in the red than hemoglobin without oxygen. Okay? So the darker red means you've actually absorbed more of the red. The lighter red means you've absorbed less and reflected more of the red. So this makes sense with what we see visually. Okay? Brighter red, the oxygen with hemoglobin. The hemoglobin with oxygen. Okay? Now, what you notice is over here there's a lot of overlap. But there's a nice clear difference here, right? And there's some difference here. What region is this? Okay, what part of infrared? Near, far, mid? Near infrared. Your TV remote control is smack dab right here. This is the wavelength that your TV remote control uses. Around 925, 950, okay? So there's some variation here and there's some variation here. And what interesting thing happens between those two regions? Between these graphs. Do you see anything interesting happening between this region and this region? It switches, they cross, okay? And that's a key point that we take advantage of when we use this instrumentation. So, some basic principles to think about. When you're measuring, you've got some constant light absorbers. Like let's think about the finger that are always present. There's always skin, there's always tissue, there's always venous blood, and there's always arterial blood. However, with each heartbeat, something changes. Okay? The heart contracts and there's a surge of arterial blood, which momentarily increases arterial blood volume across the measuring site. That means that you get more light absorption during the surge. If the light signals received at the photodetector are looked at as a waveform, there should be peaks with each heartbeat and troughs between each heartbeat. So, what we're saying here is that as the volume increases, what happens to our absorption, no matter anything that it's absorbing, what happens to the absorption if more of it is there? The absorption. If more of it is there, more is absorbed, right? So if I've got more stuff in the way between the light and my detector, I'm going to absorb more, okay? No matter what. If that stuff absorbs light, I got more of it there, a bigger volume, more is absorbed, okay? So I'll get an increase in absorption, a decrease in absorption, an increase in absorption, a decrease in absorption. And it's going to correlate directly with the heartbeat. Now, if the light absorption at the trough, which should include all the constant absorbers, is subtracted from the light absorption at the peak, the resultants of the absorption characteristics due to added volume of blood only. And in this case, the only volume of blood that's been added is arterial. When I first push, I only get this surge of arterial blood, the fresh blood with the oxygen. So everything else stays the same. I just get this bigger push of arterial. So if I take the absorbance overall, when I have that big push, that surge, and subtract the trough, that difference will only be due to the arterial blood. And the arterial blood is what I care about. Okay? That's what I'm trying to figure out, how much oxygen is in your arterial blood. Not in your venous, but in your arterial blood. So the peaks occur with each heartbeat, so it was started to be called pulse oximetry. Okay? And now you start to get a sense of why it's so important to measure the pulse. If the unit can't see that difference, then it can't get a reading, because it doesn't know if it's measuring the peak in your arterial blood oxygenation. Does that make sense? Questions about that? Yeah.
What was the basic counterpart of it?
The invasive counterpart of this, you take your wrist and bend it back. You got to find an artery, basically. You got to take blood from the artery, okay? Now, the easiest place to find an artery is over here. You guys have heard of people slitting their wrists, okay? And dying, right? Why is that effective? Because there's an artery there. Now, why do some people fail to actually kill themselves? They don't cut deep enough, because their arteries are buried deep. Why are arteries buried deep? Because we are set up so that the thing that has the highest pressure is most hidden in our bodies, okay? That's a good thing, right? Otherwise, every time we get a little nick and scrape, it'd be like, psh, there'd be this like massive flow of blood everywhere. That would be a problem, right? We wouldn't want that. Okay, you guys see what I'm saying? You want that stuff thick. That's why the arterial walls are thick. And you want it in, deep. There's only a few places where it's not all that deep. One of them is here, and one of them is here. Okay? It's still deep, but not as deep as you might like. The other spot where we have a really big artery is in our leg, but it's pretty deep. But you sometimes hear of people injuring their legs. I don't know if you guys watched the Olympics. They were talking about not Apollo Ono, but the other guy, the younger guy. Yeah, Silsky, who basically cut himself with a skate and luckily missed his artery that was in his leg. Okay? Yes.
Like 30 seconds after that artery's been severed, so 30 seconds to do that.
Yeah, you don't have a lot of time. There's a lot of pressure going on.
I think in ice hockey, there was a while ago before the goalie had the net match, one of the goalkeepers got hit by a blade and like cut his artery, and they stopped the wrestling, and that was how now goalies have
That makes sense to me. That makes a lot of sense to me.
Yeah, his trainer like served in Vietnam or something, so he like
Yeah.
took him back and like grabbed and pinched the artery, like just stuck his hand in his neck.
That makes sense, because that's what you'd have to do. You have to physically grab that thing as fast as you can and stop it. Otherwise, you just squirt out.
He was luckily on the goal next to the exit of the arena. He would have been on the other side, and since he would have died.
Yeah, you don't have a lot of time. You basically don't have a lot of time.
You can't put pressure on this because the exact pressure doesn't stop. Like pushing on it to stop the bleeding in the artery is enough to break the trachea. So
That's a good point. I didn't know about that. Yeah, it's a problem too. I mean, I'd rather live and have a broken trachea than the other way, but still, it's pretty hard. You have to put a lot of pressure. So, how did they used to measure it? How do they still measure it at times when they have to? They have to bend back the wrist and they have to get to that artery. Okay, so you can't use one of those wimpy needles that they use for getting blood from your veins. You got to use a thicker needle. Okay, it's got to be thicker because it's got to make it through and not bend. Right? You don't want the needle going. That's not good either. So you got to get in there. You got to take some blood out, and then you use a system that you might have heard about in chemistry: partial pressures of gases. There's a machine that basically can measure the partial pressure of the CO2, the partial pressure of the O2, any kind of gases that you want to measure. It takes several minutes to get that reading. How did they originally calibrate this system? The volunteer, aka sucker, was there with a device on their finger measuring the light constantly, and on the other side somebody was taking their blood, right? Or it might have even been from the same hand. They might have had a little device here measuring light absorption, taking the blood as they're measuring it, then sticking the machine a few minutes later, getting a reading, and they had to figure out what change in light absorption corresponds to a certain percentage of oxygenation. And they had to do that probably with thousands of people to validate this device, to make sure that the values they were getting were accurate. Okay? They might have done some of this on the operating room too, because they had an easier time getting access to the blood. depending on certain procedures. But they had to figure this out because eventually they now end up using this in every single surgical procedure that's going on. They've got you monitored for the oxygenation.
Does that mean to be like a big push for this?
Was there a big push for this? Well, what I can tell you is the result of it dropped the malpractice insurance for anesthesiologists in half. Okay? So those of you that want to be anesthesiologists, this made a big dent. The reason for that was because it was really hard to detect low oxygenation in patients on the operating table. The way they would detect it is the nurse or the doctor saying, oh my gosh, the patient's blue. This is a problem. The patient has lost color in their face and there's tissues. That can be too late because that usually means you're down somewhere in the low 90s, okay, or even below 90, and that can be a problem. So traditionally now, they have this machine that monitors it, and the moment they see something going down, they can immediately interject. Now, was there a big push for it? I think people were in the 60s and 70s starting to experiment a lot more with light. Remember, we take it for granted now that you can buy a little $3 red laser and you can buy a 50-cent LED. We didn't have those things. When I was a little kid in the late 60s, there was no LEDs or lasers that you could just pick up. In the labs, they had made lasers. They had started experimenting with LEDs, but it wasn't something you could just have everywhere and put in a little device. It wasn't that simple. So as they started messing around more and more with the light and having these lights that were controllable. Because remember, before, what did they have to do? If you wanted to get a specific range of wavelengths of light, you had to have a really, really bright light to begin with, and then you had to have a filter that blocked off as much as possible of the light that you didn't want to have the light that you wanted to go through. So you usually had to start with a very, very warm light source, hot, okay, that you had to be constantly cooling to draw just a little bit of that energy of those photons to come through. So that made a lot of that experimentation tough. You couldn't also just go out and buy a fiber optic readily. All these things were difficult, so you had to have lens systems. It was kind of annoying. It wasn't something you could readily do. But slowly they were able to get the data, and then eventually some of the technology caught up, and then it became easy to do this. Now I've got a student who worked with us last summer who was trying to figure out the health of teeth on animals, on dogs and cats, by having a little device that's a pulse oximeter for the tooth, and figuring out how much blood flow is in your tooth, because a healthy tooth has blood flow. So, now it's pretty easy, in a way. So, if you were going to do this, and you knew that these were the two absorption spectra of oxygenated and deoxygenated blood, what two wavelengths might you pick to measure these differences? What do you guys think? You want to find the biggest differences, so where might you measure? 680, so we got a measurement here. Why did you pick 680? Because you got a big difference here, and what else might you pick? What other wavelengths might you pick?
1,000.
Okay, 1,000. So, in reality, we end up picking these wavelengths, 660, and traditionally 940, though sometimes they pick 905 and 910. And you might say, well, why didn't you pick 680? Why didn't you pick 1,000? Cheap. Okay? Cheap light sources. So these LEDs were readily existing, cheap, and so they use those wavelengths, and you still get enough difference that you can measure what's going on. Okay? Now, so how do you do this measurement? You have two light-emitting diodes that each produce beams, one at 660 and 940. There's some variety. And then you have a photodetector that detects how much light went through the object that you're measuring. And you measure the diodes flash at approximately 30 times per second. There's a whole bunch of variation. In some setups, they flash at 100 times per second. Sometimes they flash at 30 times per second. You switch them on in sequence. So you turn on the red one, then you turn it off. Then you turn on the near-infrared one, then you turn it off. Then you turn on nothing and measure. Okay? Why do you do this? You want to do this because if I've got that pulse oximeter and I'm out in the bright sunlight, guess what? Some light's getting in at those wavelengths and making it to the detector. Because you remember what happens when the light gets in and it scatters all over the place? Okay? It's getting to the detector. You want to be able to subtract that out. And because, again, you want to make this device cheaply, you've only got one photodetector. So you don't want to have both LEDs on at once because then you wouldn't know what you're measuring. Are you measuring the red or the near infrared? So you turn on the red, you measure it. Turn it off. Turn on the near infrared, measure it. Turn it off. Turn everything off, measure it. That's going to be your baseline. You subtract that from everything else. And then the other two readings are the readings that you get for those two values. Okay? And then you get a ratio, effectively. And that ratio is going to vary with your pulse. Okay? And you want to measure it at its maximal. You want to see where the pulse is maximal and you get the biggest difference. Okay? So, excuse me. The microprocessor analysis of this light allows you to measure the arterial pulsative flow and ignore the non-pulsative component, which results from the tissues in the venous blood. And if I take the ocean optics that you guys used and I stick it on one of those pulse oximeters on the LED, and I just measure at 660 and a 910 in this case, because that was the peak for the known pulse oximeters, the ones that we used. And I measure as fast as I can. You guys never did this on those fiber optic spectrophotometers, but the software SpectraSuite allows you not only to get a spectrum, but it also can just monitor a set of wavelengths every 5 milliseconds and tell you what the range of values are. And if you do that, and you see this is at 660, and this is at 910, what you see is you see the light turning on, then it's off. Light turning on, then it's off. Turning on, then off. Turning on, then off. And it's hard to see because I don't have enough spatial resolution. That little detector is actually faster than 30 times a second. Because here I'm measuring every 5 milliseconds, so I'm actually measuring 200 times a second, but it's still not quite fast enough to get a nice smooth curve. Which is either one light's on, then the other one's on. One light's on, the other one's on. And I know you see some overlap. I don't have enough spatial resolution to separate it. But you see them both on and then a period where it's off. So this was trying to confirm, and this is how this thing works. So it's measuring a lot of light, turning off, the other light, turning off, a lot of light, turning off. It's doing that same thing. Okay? Just as predicted. And during this measurement, you can effectively think of you have a constant component of light absorption that's due just to the tissue, the bone, all that stuff, right? Because there's stuff in there that just absorbs. You got the constant light absorption due to the venous blood, which is still in there. You got the constant light absorption due to the non-pulsatile arterial blood, because there's still some arterial blood in there. But really what you're measuring is a variable component, which is due to the pulse. So that's the piece that you're measuring. Okay? Now, the microprocessor analyzes all these components, does a subtraction, and the reason it uses these two wavelengths is because they have very different absorption characteristics, and then it uses that ratio, as we mentioned before. So, just to show you the change in the arterial blood flow, that it does lead to a difference in absorption, I took the ocean optics again, and I just stuck my finger out towards the sun, because the sun has red light in it, and I put the fiber optic behind my finger, and again every 5 milliseconds I measured, actually in this case it's every 15 milliseconds, with some smoothing, just to see, can I see the change in absorption due to my pulse? And this is a span of 55, this is 5 seconds. So in 5 seconds I had 1 beat, 2 beats, 3 beats, 4, 5, 6, 7. So that means my heart rate was, you guys figure that out? What was my heart rate? This was 5 seconds. I had 7 changes. What? What do you guys think? Does that sound right? Okay. There's 12 5-second increments in a minute. So 12 times 7, 84. So my heart rate was 84. So as you can see, even with that little simple setup, I could see the pulsing of my heart. There was a change in absorbance. It wasn't huge, but it was there. Okay? And that little device is measuring that change. Now in this case, I only measured it at one wavelength. I measured it at 660 rather than at the 910 or 940. Why do you guys think I might have picked the 660 rather than 910, 940? Believe it or not, the detectors are more sensitive, so you get a bigger peak. Okay. Also, if you guys remember in the graph, there was a much bigger change in absorption than there was at the other way around. Okay. So that's why this one was convenient to use. So, where do we use pulse oximetry? Well, we use it a lot in the anesthesia room. Okay. Monitoring care during consciousness and sedation. We use it in the post-anesthesia care unit to see if your body is recovering after the anesthesia. Intensive care units, we use it a ton in neonatal. So intensive care, newborn nursery, delivery studies. It's also used when you bring a patient from one part of the hospital to the other. Right? In the diagnostic lab, where they're testing how well your lungs work. In the exercise lab, in the sleep lab. Sleep lab, they use it a lot to look for things like sleep apnea, where you're not getting enough oxygen, okay, and you're disrupting your breathing. Subacute care centers, home care patients, other patient conditions, and it's also used a ton by pilots. Private pilots, yes.
How much is the small pulse?
A couple $100. You can now get some for about 150. I don't know, how many of you had a chance to see the other one that we had that shows the actual waveform? Did any of you get to see that? Okay. I want to show you quickly this little device that I'm going to pass around. This little device is a pulse oximeter, but notice that what it does, it shows you the value. This is actually cheaper than the other one. It's a newer one. Let's see the heart rate. You can see the pulses. You guys see that? And I'll pass this around. If it turns off, just press the white button again, turn it back on. So it says 98% oxygenation. There's my heart rate, 92. And there's the pulsing. Okay? And this one has the capability of also monitoring. You can actually record the values. So you could use it over time. The other thing I wanted to pass around for you guys to see is this is what they use in the hospital. They even have a little picture of the finger there. They put the finger like this, and they fold it over, and then they tape it onto your finger, and then this plugs into a machine. Okay? And then they throw these away. Okay? But this is from a company that does a lot with this, Massimo. And this one, basically everything has been built in there. All they're doing is supplying power and getting a reading out of here. So there's the LEDs in there. Both LEDs are in there. And the photodetector is in there. Okay? So take a look. Here, I'll pass it this way. Okay, so, yes. It probably costs them, I mean, they're not even using a fiber optic there, they're just using electrical wires, which is even cheaper than a fiber optic. So I'm guessing it costs them less than a couple of dollars, but they're probably charging 10 to 15 to the hospital. Usually a device, the charge is about, the charge to the people, like to the hospital, is usually 3 to 5 times what it costs to make for a medical device. That's pretty normal. And then usually the hospital marks it up as well. So, you see what I'm saying? So the maker, the designer charges X, they charge the hospital 4X, and then the hospital charges you another 2X or 3X on top of that. So there's a lot of markup, a lot of mouths being fed through these kinds of things. Okay, now, sounds wonderful, right? Sounds like this stuff is just perfect, cat's meow, not invasive. Yeah, there's no fiber in there. They don't even use a fiber. They don't need to because the detector is on the finger. Everything's on the finger. All they have to do is send electrical signals. That's all they have to do. It makes it even more reliable. They don't have to worry about kinks. They don't have to worry about any of that stuff. So literally they have the light on one side that they control electronically, and they have the readout on the other side. I mean the pickup. So things can go wrong with this type of device. Oh, you can pass it down. Others can see it too. Okay? So, what are some problems? So some people have cold hands and feet. I'm sure you've known. You may yourself be one of those people. What does that mean, cold hands and feet? Not as good circulation, which means there's not as much blood flowing through, which means there's not as good a signal. Okay? So your readings might not be as accurate. Now, which means you may not give them to Gattaca. Well, they probably can get some blood out of you. But anyway, so it is really important for all of these devices to be considered accurate, for them to be able to say if the signal is strong enough. So on the one that's passing around, there's a little indicator that goes up and down that it has to monitor to see if there's enough signal. So what are some possibilities where you might not get enough signal? We said cold hands. What is another possibility? You've lost a lot of blood. Any other possibilities?
If your subject is purposely holding the breath just to see if they can make it go down.
It's actually pretty hard to affect it, though,
Yeah,
believe it or
I
not.
noticed
I know you guys have
that.
tried. Many of you guys have tried. It's really hard to do that. Any other thing that might affect? What other reasons might have little blood in the path of the light? What about if you just have very little hands? Like if you're a child, right? You'd have to compensate for that. So basically, these devices have to check for enough signal. An irregular signal can also cause problems. So how can you get an irregular signal? Your heartbeat's irregular, so you go boom, 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 boom. If you've got that kind of thing, it has to detect this steady pattern, right, for it to be able to get a reading. If it doesn't get that, it won't be able to get a reading. What if you're like, yeah, let's get a reading? You know, it's hard, right? You're moving. The light's moving, right? This thing's moving on your finger, okay? So what happens? Now you guys laugh, but that's what they have to make special units for athletes, right? How can athletes monitor this while they're running at top speed or swimming or doing all these other things? They have to create a device that would be consistent enough to get a reading. You guys working on getting your heartbeats up, or what's going on right now?
So what does the graph on the bottom show?
Grab the bottom of your heart.
Okay. But then when I move, it's like.
There you go. See, she's proof of what I was just talking about a few moments ago. Now, what might be? Can you raise up your hand so the rest of your class can see your hand? What might be causing her problems? Show your other finger. What might be causing problems with her reading? Aha, nail polish.
Good attitude's a vampire.
Now, why might nail polish cause a problem? Yeah, do you guys remember one of you brought the nail polish? We have a picture of the nail polish over there. You had a nice glittering nail polish. Was it you that brought the nail polish? Who was it? Yeah, it was you. Now, that had nice little metal particles in there that made it nice and sparkly. Okay? What would that do to your red light trying to get through the finger? Scatter it. May not get very much to go through. And therefore, you don't get a reading. So one of the things they do when you go to the hospital is they get rid of your nail polish.
Do they get rid of all of your nail polish or just on that finger?
It's a good question. I don't know. Never had that issue. So now,
Plan on getting injured. Don't have a manicure right before.
yeah, don't get a manicure right before you get injured. Yeah, or at least a fancy one. You know. Now, a lot of nail polishes don't do anything. They're transparent to those wavelengths. They don't have enough of an effect, but some do have an effect. The other thing can be poor positioning of the probe, and it's a particular problem with very small fingers and very large ones. Right? If you have a really large finger, there might not be enough light to get through. If you have a very little finger, there may not be enough blood there to get a signal. Right? So those are problems, but there's also some other major limitations. And that is, oximetry is not a complete measure of respiratory sufficiency. Okay? So if you have hypoventilation, poor gas exchange, you could have 100% oxygenation, but your tissues have a hard time getting the oxygen out. Okay? So you can have excellent blood oxygen levels while still suffering from respiratory acidosis due to excessive carbon dioxide. Okay? It does not talk to you about how good the exchange of gases in your lungs are. This only tells you that the blood that it saw had a lot of oxygen in it. But if your lungs are inefficient at exchanging the oxygen and CO2, you could still have a problem there. Nor is a complete measure of circulatory sufficient. You could have 100% oxygenated blood, but very little blood. That's still a problem, right? If your body needs a certain amount of oxygen, but you've only got half of that being delivered to it, your arterial blood is fully oxygenated. It's as oxygenated as it can be, but there's still not enough oxygen being delivered to your body. Okay? And also, When you use a 2-wavelength saturation level measurement device, like the one that I passed around and most of the ones that are inexpensive, they only use those 2 wavelengths. It cannot distinguish between carboxyhemoglobin and oxygenated hemoglobin. So, what does this mean? Hemoglobin has a very, very, very strong desire to bind to CO, to carbon monoxide. And it can bind it and be bound up. It's done. But it still has a color, actually kind of close to blood with oxygen. Close enough to blood with oxygen that if you have carbon monoxide poisoning and you get the pulse oximeter put on your finger, it still looks like you have perfectly good saturated hemoglobin, but in effect you might not have very much at all because all your hemoglobin's been bound up by carbon monoxide. Okay? So, if you're in a fire and you breathe in a lot of smoke, a lot of carbon monoxide, you actually need additional wavelengths to distinguish between the carbon monoxide and the oxygen to determine the blood oxygen level. Because there are places where that difference is pronounced, but they don't happen to be at 660 and at 920. Okay? So in a carbon monoxide, this is one of the reasons they ask you when they put one of these things and you're having problems breathing, they'll really want to know if you've been in a fire. Because if you've been in a fire, they have to put a more sophisticated device on your finger that measures multiple wavelengths and to be able to distinguish between those two. Does that make sense? So in most cases you're fine, but in a few cases you're not. And then some other limitations. When you're getting supplementary oxygen, you may be getting plenty of oxygen, but you're not clearing out the CO2. So again, your oxygenation might be fine, but you may have another problem where you have too much CO2 building up in your blood. It doesn't distinguish anything about CO2. Okay? So it doesn't mean you're healthy just because you get a good reading there. That's the bottom line. So, carbon monoxide, they show it as oxygen approximation because of how carbon monoxide interacts. Methemoglobin. It's an abnormal type of hemoglobin that does not bind oxygen well. Normally, 1 to 2% of people's hemoglobin is methemoglobin. A higher level will tend to cause a pulse oximeter to read closer to 85%, regardless of the true level of oxygen saturation. So you could go in, get this thing on, measures 85%. They think you're about to die. Okay? Everything gets brought up. The reason it's showing that is because you happen to have an abnormally high level of methemoglobin, which is a genetic condition.
The body looks for the CO2 concentration, like one thing that's
So you're saying, why don't we have a pulse oximeter that measures the CO2 in the blood?
Why do we think that's the body looks for CO2 naturally?
Oh, the body needs CO2, but the CO2 is waste that we need to get rid of.
The body needs CO2 to measure, like, if we're out of breath, it's like the CO2 concentration, but it's like the absence of oxygen. So, why does
If you're running out of breath, you're trying to figure out.
Well, if you're running out of breath, it doesn't your body say that you just need CO2 there, you need more oxygen, not there's no oxygen there. So,
You're saying how does the body itself respond physiologically?
well, I think the body looks at the CO2 concentration. So why don't we say the life that
Why wouldn't we create a device that measures CO2?
the body,
I mean, ideally you wanted to measure both, right?
yeah.
Okay. Now, are you measuring oxygen, or are you measuring some other property with the device that you've seen, pulse oximeter? What are you measuring? Are you measuring oxygen? So are you measuring oxygen? You're measuring bound oxygen to hemoglobin. There could be other oxygen in your blood. I could be pumping oxygen. I could have a little thing on the side that's pumping oxygen in your blood. It would probably interact with the hemoglobin because the hemoglobin likes the oxygen. But if it didn't, I can't measure that. So I'm not measuring CO2. If I wanted to measure CO2, I'd have to find something that the CO2 binds to that causes some kind of color change. Because otherwise, CO2, do we see CO2? So it doesn't have any optical properties in the visible range. There's other wavelengths that we can get at with the CO2, but now it starts getting much more complicated. So the easiest thing to measure is bound oxygen because it causes this dramatic, not ultra dramatic, but relatively dramatic change in the hemoglobin. That's why we measure that. Ideally, we measure a whole bunch of other things. Okay. Now, some other things. Skin color. Darker skin types can have inaccurate readings when levels are below 80%. So basically, it's the same idea as the nail varnish. Anything that gets in the way of that reading, nail polish, intravenous dyes, so you're doing some other kind of procedure and there's some dye in your body, strong external lights, electrical interference, all those things can cause problems with the reading. Okay? If I got a really bright light coming in from the side, it might overwhelm the signal that's coming from the LED.
So if you have unusually high levels of hemoglobin, how do you measure the oxygenation?
No, so, I mean, you can do it invasively, but there's, again, a fancier device that Massimo, that same company that I sent that piece around from, they make a device that actually uses 6 to 8 wavelengths. And it does use a fiber optic in this case. It doesn't use this little inexpensive throwaway piece, but it uses a fiber optic that goes in and measures all those different wavelengths. And then, really, the way you discern more species in your blood is you have to find more points of color to check, more points of absorbance to check, and look at those ratios. And they are now sophisticated enough where they can look at 6 to 8 different wavelengths and be able to distinguish methemoglobin versus carbon monoxide poisoning versus actual oxygen saturation in hemoglobin. Okay, good question. So, here it is. That's the latest and greatest, one of them. At least this was the latest and greatest little back. You can see it's that company. This was their portable unit. This is their hospital unit. So this employs 7+ distinct wavelengths. At some point, they don't want to tell you, right? Because it's their trade secret of what they're using to do this. But it can actually accurately measure carbon monoxide and methemoglobin in the blood non-invasively in seconds. So again, you see the rate, see the pulse rate going up and down, up and down, up and down. And this can measure, and there's your oxygenation, and then it's telling you the other things too, concentrations of the other species as well. So you know whether you have a patient with carbon monoxide poisoning, you also know whether you have someone that has a high methemoglobin content. And it can discern all those different things. And then one of the last things I want to show you about pulse oximetry is just as much as I can figure out how much oxygen is in your finger or in your ear or through your eye, I can do the same thing with, is there oxygen flowing in parts of your brain? Okay? So this is a cutaway of a skull, okay, a drawing, representation. Here's the skin, here's the bone, here's the brain. And if I put really, really bright light source, the way light travels in your brain is in the shape of a banana. Okay? So if I make a really bright light source here, they have determined that the majority of light, the way it scatters and interacts with all the bones and tissue and brain, is it comes back from the surface about 30 millimeters away, 3 centimeters away, and then comes back from deeper parts of your brain about 40 millimeters or 4 centimeters away. So they know roughly that's where the majority of light comes through. Now, of course, the light's coming in like this, it goes in a circle, right? It doesn't just come out one particular spot, it's in a circle. But if they can make a light, a bright, bright light, what color light are they going to use? Red and near infrared. That's what we use for pulse oximetry. They can pass it through your brain and effectively tell whether in that portion of your brain there's fresh blood. And the reason we care about that is because, you guys ever heard of MRI? And how about fMRI, functional magnetic resonance imaging? Okay, so MRI, you guys have seen all those pictures. They give you slices of the structures in your brain. What they're taking advantage of is a property of oxygen. The oxygen has the hemoglobin has the iron in it, and they can actually measure where that is, where there's blood, okay, in your brain. And they use that as part of the imaging modality. In functional resonance imaging, they're looking at movement of blood in your brain. Okay? By literally saying, if brain is going to a certain part of the brain, if blood is going to a certain part of the brain, if blood is going to that particular part of the brain, it means that that part of the brain is active. It's working. Okay? And they've actually shown when they take these images and they take them in fast succession, they can see different parts of your brain taking in this blood. And then it dissipates again. And then it goes to a different part. And they can show activation of different parts of your brain. It's like your brain is shunting the blood to the parts of the brain that need to be active to perform that mathematical calculation or see or process auditory simulation. Okay? So, the same idea goes with this. If we shine light and this part of the brain is active, we should see some kind of change over time. And because all we're doing is shining lights and measuring the stuff coming out, we can do this very quickly. And we can look for changes. So, what do? We put a little skull cap on you. The little skull cap has 4, 8, 16 really, really bright lights, sometimes lasers, sometimes LEDs, with little detectors at the appropriate distances. We pulse that light, same way that we do with pulse oximetry, and we see how much is coming through, and then we make a map of where there's activity in your brain. We can actually see if you're activating parts of your brain versus other parts of your brain. Not very high resolution, several centimeters of resolution, whereas fMRI can get you a millimeter voxel, a millimeter by millimeter by millimeter kind of cube in space. This only gets you like a centimeter, a couple of centimeters area. But it's good enough that we can put this on a premature infant, make a loud noise, and see if the right part of the brain is activating, or shine a light on them, or do something. We can see if there's actual brain activity. And the way that one works, the neonatal one, is just literally a little pad that you just stick on one side of the brain, stick on the other side of the brain, and you see if there's any kind of motion of blood which indicates activity. Much easier than an MRI or an fMRI, and shows you activity right away. Okay? Questions about that? So, with that, that's it for pulse oximetry. Okay? Any questions in general? I have a question for you guys. Why is it pulse oximetry? Why is it called pulse oximetry? You measure with the pulse. Why? Why do we care about the pulse?
Because when the pulse goes up, when the new arterial blood comes, and there's no oxygen in the blood, you can see the difference in the oxygen.
So when we give you that value, 98%, 99%, whatever you guys read when the thing came around, you put your finger in it, is that the maximum, the minimum, what is it, of oxygen in your blood, in your arteries? Is that 98, 99, is that the maximum amount of oxygen in your arteries or the minimum amount of oxygen in your arteries at that moment? Okay?
Maximum?
It's the maximum. Okay? Remember, for most of us, the stuff going back is at about 75%. Okay? So we're measuring the peak, and we're getting it through that heart rate. Okay? What wavelengths do we use to do this on a basic model? Okay? What do we have to do if we want to detect some other species like methemoglobin and carboxyhemoglobin? Add more wavelengths, okay? And what happens to the spectrum of oxygenated blood and deoxygenated blood in the region that we measure? They cross. The absorption spectra cross. Okay? Okay, does that make sense? Okay, with that said, here's where we are in terms of our presentation. Today, the photon fighters will go briefly right after this class. You guys are all set? Tomorrow, we have the Jetties of Light. Yeah, we'll be going to Woodland with Professor Shackelford. You guys need to pick up your materials sometime later this afternoon. When will you guys pick up your materials? You may be using some of the same materials that they need. So you likely have to come later. You can tell me right after class. Just think about it for a moment. Then we have Benicia High School going on Thursday. Team Benicia. Okay. And you guys still... Team Benicia. Okay, so you guys are going to probably pick up Wednesday after class. And I'm trying to arrange the time for H2N2. I haven't heard back yet from the teacher, but I'm assuming there's some flexibility. It will be in the morning. Okay, and you guys said you were okay with that, right? In the morning? Okay? So, Now I'd like the two groups that already presented to come up. Why don't we have Team Cedric come up first? And why don't you tell the class what you guys discovered? By the way, all the pictures taken are being put up on the Flickr site. And if you guys have pictures that you took, because I wasn't there for all of you guys, if you have pictures that you took that you would like to share, please get them to me. Okay, come on up. Take center stage. Come on. Okay. So.
How you all doing tonight?
Not yet, I hope.
We happened to have our presentation during the protest.
Yes.
That's not a big thing.
That was interesting.
Yeah.
So we had a lot of bored people come out looking for something to do. People like candy. It wasn't really surprising, but it was good to have it confirmed. And glow sticks.
So roughly how many people do you guys think came through?
Probably,
I guess they're like 50-ish.
yeah. They wanted to see pictures of the protest in infrared.
And what worked the best for getting people to come and pay attention? Like, what did you guys have to do? What did you try to get people to come and talk to you?
Hi, this won't hurt. Give us your finger.
Okay, did that work?
Yes, actually.
Okay, what else?
The lab coats actually attracted a lot of people to come out of this for like, what's with the lab coats? Those, they could really get people.
Okay, so lab coats worked. And then you guys went out there and grabbed people. Okay. How about the infrared camera? How did that? Did that help?
Screening see the protest
some
in
people,
infrared actually was very popular.
Okay.
Like when they're marching by, so when you walk out, so they can watch them on the camera.
Okay. And what did you find to be the hardest thing?
The laser cam thing we had some trouble with, just
to get the diffraction pattern and whatnot in daylight and limited space.
it didn't
Yeah.
work.
So did you stop doing that?
Yeah.
Okay.
And the microscope and the wind wasn't being very cooperative, so it was hard to focus. And since it was really bright out, you couldn't quite see the picture on my computer screen as clearly as you.
You guys see how they were set up? They had the poster, they had the stuff there. Here they're showing off the images from the infrared camera. Variety people came by.
We had several sore types of glow sticks and so trying to.
So you guys were fortunate to have a high density of people coming by.
Yeah.
Here's the protests that were going on.
Also, a lot of people handing out stuff. So you say, "I'll take your flyer if you come do something at our table."
Okay, so they use the tit for tat mechanism. Okay, and what did you guys find most interesting about this experience?
We wandered over, like, hey, you have a poster. I have time on my hands. Tell me about it. Cool.
The thermometers don't work unless you keep them warm.
Yeah, this is something that was discovered. It was cold outside, so unless you keep the thermometers like hidden in your pockets or something like that, they just don't work. They're too cold themselves to be able to take the reading. What else? What do you think about trying to get your fellow student members interested in something different? Is that an easy process, a hard process?
We had plenty of fun toys, so it was pretty easy.
Grabbing people with what we always work.
Okay. And let me think. So what do you think was the one most popular thing or easiest to get people interested in?
Either a pulse oximeter or
The pulse oximeter was the easiest, just like the quickest
Just
thing to
quick.
get people to do and get them interested.
The infrared camera was pretty fun.
That's pretty easy.
Okay. Thank you guys. Good job. Okay. Let's get the marketeers up here. Let me see. I got a couple of pictures of the marketeers. I don't have as many pictures of the marketeers here. 1 second. Where did the marketeers go? Sorry, 1 second here. Let me get back to the pictures of the marketeers. Let's see, where are they? Okay, here's one of the pictures of marketeers. So tell us what you guys did.
Okay, so we set up a booth at Farmers Market on Pig Day, which, yeah, there were a lot more people, but we got there at like 7:40 in the morning, and we're all the way down at the end at that time.
So they were past the playground. I don't know if you guys know where that is, but near the museum.
One like other one set up past us, like
Yeah.
as we were about to leave.
Yeah, like at 9, someone else finally came to our left, but.
So we were at the very end, so we didn't get that many people. Plus, being at Farmers Market, a lot of people walked on by in order to do something else. But we did have a lot of people stop, especially with our poster. You can't really see it in these pictures, but we had the big, like a purple poster showing a lot of the diagnostic stuff. And that was a big hook for a lot of people.
Yeah.
Like they'd see that, slow down, and say, "Hey, you want to come over or take a
Yeah,
test?"
while they're looking at it, we're like, well, since you already stopped, here, take a handout, and we'll start talking to them, and they can't leave.
It's the people who just look straight ahead or just glance over you and keep walking, and you really don't have a chance of getting them to stop.
Yeah, there's the poster. That's after I left, but I also had brought my laptop, and we had the video of the HIV transmission to another cell. But it was kind of the sun, there was glare, so it was kind of difficult to see unless you're standing at the right spot. But when people could see it, that was pretty interesting for a lot of them because, HIV is like one of those big name diseases.
So how many people do you guys think you had come?
Around 50 probably over the course of the day. A lot of them came in groups. It was the thing, like you have 5, 6 people at the same time with one group, stop by and talk for a couple minutes. But most people would stay maybe at most 2-3 minutes, and then they'd want to go and do something else. We had a couple people who would stay for longer who were interested.
There's that one guy that like
Yeah.
Yeah.
3 times.
He was really interested. He was like volunteering for something else too, but like he stopped by and we gave him like the whole spiel, and then he left, and then he came back again, and he asked more questions, so that was cool. But there was like a finger painting booth or something kind of to our right, so we were upstaged by it. A lot of people were going there.
So what were the rough ages of the people that you think mostly stopped?
Older people.
Yeah.
I think
we
that's,
had the
yeah.
like health thing, so they like.
And also because that early in the morning, typically the college students probably didn't show up until like 10 or 11, while the older people, early to rise.
And the big day, a lot of people stayed down.
Yeah.
The pigs and the kids.
So what do you think people were most interested in of the things that you had to present?
I think a lot of them were interested in like the diagnostics. We had a few groups that came by who were really like into the pulse oximeters. She goes, "Oh, I recognize that from the doctor. I've seen that around. So they use this, right? So this is actually something that's in practice now." I think a lot of people were interested in that.
Yeah, and then the thermometer. One lady came by, she had like 2 kids, and she's like, "Oh, I know that. They use that at the hospital. I wish I could get that at home," kind of thing. So that was cool that people actually recognize the instruments.
Yeah. And we did have quite a few people who were familiar with CBST and things.
Oh, really?
Oh, yeah.
Yeah, some ladies who worked
There's
there.
2, I think, right? Yeah, 2 ladies came by in the morning, and then they asked us who our teacher was, and we told them, like, "Oh, yeah, we know him."
Oh, interesting. I wonder what that was. And you worked on a handout, right?
Yeah, I just, it was just a 1-page thing that like summarized some key points about
Yeah, I read it. I'd like you guys to send me that, by the way.
Oh.
Send me the file. Okay, so what did you find was the most interesting thing for people? Like, what's one, if you were to pick one thing that was the most attractive to people or that they seemed to engage or ask questions on, what would that be?
They were pretty interested, I think, the pulse oximeter, because we told them, like, if we don't use this, like, we'd have to, like, stick a needle in you and take blood. And so people were much happier to have, like, their pulse rate and their blood oxygenation done in, like, 5 seconds as opposed to a whole thing. And then I think the HIV thing was pretty interesting because, it's, like, working toward a cure, kind of, so.
Yeah, they're interested a lot in like how far research has gone, and that kind of thing. Like how soon can we see this actually being used with HIV and cancer stuff.
Now, how did you guys respond to that?
We said right now, it's just starting. It's still in research. It could be a while, but they are doing tests and it looks promising.
Okay.
I think someone asked about like the ethical implications of this, and so we said that they're still killing animals, but not as many. Yeah, because we can test one animal and keep it alive throughout the whole study instead of killing the rat every week or whatever.
Oh, okay. Okay, so there were questions around that. Okay. So what did you find the most challenging thing of putting us on? Other than waking up early in the morning.
It's hard to get people to stop a lot of times. Especially, you'd see these people and they just then so we're gonna just keep walking and keep trying to bring them over. So, and that was kind of a pain. But some people, some people were really friendly. They'd stop by and actually be genuinely interested. So.
Okay. Okay. Well, thank you guys. Good job. Okay. So with that, you guys know I'll be asking all the other groups that we can potentially get to say something about their experience. It's going to be tough for the Thursday and Friday groups to say much, but just I may have you guys just say something really quick right before the exam, just a minute or two, just so we have some sense of it. And make sure you guys and Benicia, you guys need to either videotape.
Yeah, we're gonna videotape.
Okay, that'll be interesting to see.
Make another quick time.
Okay. So, what we're going to do on Wednesday is we're going to go through every single lecture quickly and just look and hammer the main points. And have you guys ask me questions, okay? That's the main idea. I'm going to go through the PDFs, the same thing that you guys have when you take them off the web. And we're just going to go through very, very quickly and figure it out. We've done this every year. It works. But come prepared with questions that you might have ahead of time if you have some questions that you'd like to address during that time. And then we will have our final 1 week from today, as you guys asked for. And hopefully we will be able to give you back your reports at that time. So make sure that you turn in your reports today. They're due by the end of the day. And remember, put your name on the actual file that you send me. Your last name and then lab report 2. And ideally give it to me in doc format or PDF, okay, not docx, just to save me a step. Make me that much happier. Other than that, if you guys have any questions about what we talked about today? Otherwise, there are groups that need to pick up stuff sometime today. Just stay behind for a few moments so we can talk about it for a second. And I also need to talk to you for a moment about making up that quiz. Okay? So, you guys have a great day.